Go ahead.
Good morning and hi everyone. I am Andrea Ruggero from University of Pisa, and I'm here to present you our method for active space debris removal based on expanding foam. As you definitely already know, space debris are becoming in recent years a major issue for the survivability of spacecraft in the LEO region. And as a matter of fact, this happens because a lot of satellites are orbiting this region since they've never been disposed. More or less, the 85% of the 6,000 satellites that have been launched in the last 50 years are still in this region. Moreover, the random collision that can occur between these space debris can even let the debris population grow, the so-called Kessel syndrome, and this can further complicate the access to space in the future. For these reasons, the development of an active debris removal system is definitely an essential task to perform for next year. Several debris removal methods have been already proposed: electromagnetic methods, capture methods, remote methods, and momentum exchange methods. And the one we are proposing is can be classified as momentum exchange methods. Is based on expanding foam. We exploit this foam to obtain a huge increase of debris area to mass ratio, and to exploit drag, atmospheric drag, to obtain a significant reduction of the orbital lifetime of these debris. Just to give you a brief overview of the method, we have a orbiting platform equipped with a foam ejection device and the target debris. The platform is in charge of performing a rendezvous with the debris, and then to eject some foam on the debris, creating a sort of foam ball that encloses the debris itself. Then the platform can leave the debris orbit and chase another debris, leaving the last one free to the orbit by itself under the influence of atmospheric drag. Well, so the foam ball is nucleated all around the debris, and the atmospheric drag is in charge of decelerating it. As is obvious, this method has some pros and cons, and some of the pros is that it's a passive method, as Leopold said before, and we have this foam that is moderately static with respect to impact with other debris, and it's totally based on atmospheric drag that is costless. And we think that this method can also allow to tailor the size of the foam ball with respect to orbital and physical characteristics of the debris. We don't require any docking, and besides, we have a low technology readiness level, and we have, since we cannot neglect the mass of the foam, the mass of the system composed by the foam and the debris increases with drag exposed area. Well, we almost every day get in touch with different kind of foams, and foams is actually the key aspect of this method. And any foam can be classified considering these two parameters. They are the internal structure of the foam and the material they are composed of. We have identified, considering the internal structure, open cell foam as the most suitable one for our purpose, since they usually have higher expansion factors. And considering the material, we have identified polymeric foam as the most suitable. As a matter of fact, these foams usually are more light and versatile than other kind of foams. And in particular, two component polyurethane foam have been identified as our best candidates. They can easily tailor it in terms of physical characteristics for any application, and they are easier to obtain and handle also in a harsh environment like space. Well, so what we would like to obtain is a huge expansion factor, as one you can see here. Obviously, the expansion factor is the ratio between the final and the initial volume of the foam. And for this reason, we developed a foam expansion model. This model is a first-order model based on a single bubble wrapped within a polymeric matrix. And this bubble contains all the gas that is created during the chemical reaction between the two components of the polyurethane foam. This bubble starts growing due to an initial pressure that exists between the inside and outside of the bubble. And as soon as this difference between inside and outside vanishes, the bubble stops growing. We have then identified some target physical characteristics for the candidate foam. We would like to obtain a density of 1 kilogram per cubic meter and an expansion factor of 1000, and we can compare these values with one of the state-of-the-art for ground-based application that span from 6 to 19 kilogram per cubic meter for the density, with expansion factor from 10 to 300. The density value we identified is also very close to the one of the lightest material I have developed, as aerogel, that has already been used in space for the collection of dust for the Stardust mission, and I'll give you some more details this afternoon also for this. Well, then we have used 3 different debris data sources to test our method. One provided by ESA as a filtered list of the discus list. One is a proprietary list of some synchronous objects, and one is a filtered list provided by Union of Concerned Scientists. We have a total of 427 objects, and that span over a broad range of physical and orbital characteristics. We have here plotted the mass of the debris, the mass of the debris that are orbiting, that we have targeted, with respect to the orbiting time after the forming process. And we can deorbit more or less the 93% of them within 25 years, that is the limit stated by ACT-Pisa, and about 71% within 10 years, and 42% within 5 years. At this point, we decided also to model an active debris removal mission with a deorbiting platform equipped with a low thrust, with an electric thruster, and this platform would weigh more or less 4.6 tons. That's compliant with the payload for the Soyuz launcher at an altitude of 900 kilometers, and is equipped with 12 kilowatts of solar arrays that would operate to Hall effect thruster to PPS 5000 thruster. And the platform is obviously equipped with a foam ejection device, as I said before, and we have identified this candidate foam ejection device among several options, and the one that is the most suitable from our point of view is a spray nozzle mounted on a robotic arm. And then we decided to, let's say, test the performance of our method in considering the 50 degrees of the discus list. And we have seen that just 7 missions are required to target all these debris. And here you can see the propeller mass consumption for each maneuver required to go from one debris to the next one, the maneuver time required, and the foam mass required for each debris. And here you can see the red line that splits one mission from the other. Well, on average, we have seen we can deorbit about 11 tons of debris per each mission, and with each mission would last more or less 4 years, with 1.6 debris per year deorbited, and with a mass of 2.5 tons. In conclusion, we have proposed and analyzed this innovative active debris removal method. We identified this candidate foam, a polyurethane foam, identifying also its target characteristics, and we've seen that we can save up to the 80% of the original deorbiting time of these debris applying our method. Our low thrust mission analysis also showed that we can on average deorbit 11 tons of debris per mission, and we also think that a simplified version of this method can also be used in near future, as a self-deorbiting device for spacecraft that can be launched in order to mitigate instead of clean the space. Thank you very much.
Okay. Well, thanks very much for